Hello, linear algebra students. I've had many questions about span from different students, which is understandable. It's a new concept for us. So I just wanted to talk about this some and then do some examples. Okay, first of all, this is the question. What is the span of vectors in Rn? Well, in words, you take all linear combinations of some collection of vectors, but I want to understand this geometrically, all linear combinations. That's one thing to say. Another thing to say is the span of some collection of vectors. This will be a subspace of Rn. Now let's look at some pictures. So here I just have arrows. I have V, W, and X, just depending on the picture. And these could be in any Rn. First of all, what's the span of one vector, non-zero, vector V? Well, you just have one vector. The span, all linear combinations, it's all multiples. So for instance, I could take, that would be maybe 2.2 times V, and then you would stretch out that whole line. And you could take negative multiples of V, and this would stretch out back this way. If you have one non-zero vector in Rn, and you take its span, well, you just get a line. This would be a line. And through the origin, this would be a line in Rn. It's a one-dimensional subspace. Okay, now, what about if I have two non-zero vectors, V and W, but W is not a multiple of V? So in this picture, W and V are linearly independent. Another way to say that is we have no redundant vectors. The question is, what do I get when I take all possible linear combinations? Well, one linear combination would be, let's think parallelogram rule for adding. You could just take V plus W. That's one of them. That would be, say, this vector. Okay, but that's definitely not the only thing in the span. We could have all multiples of V, which would trace out this line. We could have all multiples of W, which would trace out this line. And then, well, all linear combinations. So I'll say AW plus BV, where A and B are real numbers. So in particular, let's pick our favorite point here. Let's pick this. Can I write that as a linear combination of V and W? Sure, let's figure out what it would be. Let's take, here is some multiple of W, and then there would be some multiple of V. So I'm not sure, maybe it's minus 1/3 W and then minus V. That would be the linear combination. Just think about adding arrows. Okay, so that would be this vector right here. Okay, and you could do that. Pick your favorite vector along this iPad, really. And here, could you write this as a linear combination of V and W? Think about adding arrows. Once again, sure, it looks like 1, 2, 3 V, and then maybe minus 1.5 W. That would be that. Okay, so when you have two vectors that are independent, linearly independent, we can see what happens with the span. We're going to get all of this. Okay, and this is a subspace. We get a plane. Maybe I will just write it as this way. This would be a two-dimensional subspace of Rn. That's what we would get. Okay, but there's another possibility here. What if W is a multiple of V? Here I have W as a negative multiple of V. But you see what happens here. So let me just mention that this vector W is redundant. W is redundant. And what happens when I take the span? Well, you see W is already in the span of V. It's a multiple of V. And so here, I do not get a plane as I did in this example with two vectors. I will just get a line, and it will be this line. So here I get a line or a one-dimensional, maybe I'll say it this way, but it's the same thing. It's a line. It's a one-dimensional subspace of Rn. Because of the redundancy, note that in this example, I only have one linearly independent vector that you can take as vector V. Now, In the bottom row, I'm looking at all linear combinations or the span of three vectors, VW and X. Again, these are in Rn. And so the first situation, now, of course, you have to understand I'm drawing on an iPad, which is fundamentally a two-dimensional thing. But in this situation, VWX are linearly independent, meaning that this X is not on the plane spanned by V and W. Okay, gives you another dimension here. So it's going to be very similar to this. If I just took all linear combinations of V and W, I would fill out a plane, but now I have X. So for instance, I could get a point up here. You could figure it out, whatever the multiples of V, W, X you need to get that, thinking about adding arrows. And so we would fill out this whole three space. So here, we have a three-dimensional subspace of Rn. If the vectors are in R3, then this would equal R3, but it's a three-dimensional subspace of Rn. And in this example, I'll just mention that this V, W, X, they are linearly independent, the vectors, linearly independent over here. Okay, now, this is not the only possibility. In this example, X is redundant. So let me mention that this vector X is redundant, but I do have that, say W is not a multiple of V. Okay, we see it looks like V plus W is X in this picture. So I'm not going to add this third dimension by taking the span. If I take all possible linear combination of V, W, X, it's just the same as taking all linear combinations of just V and W, in which case, maybe I'll make this one yellow. You just get this plane. So once again, when you have one redundant vector in a collection of three and two independent vectors, as we see here, we will have a plane. So a two-dimensional subspace. Even though we're taking the linear combinations of three different vectors, it's because we have a redundant vector. We have a two-dimensional subspace, again, of Rn. But even more so, in this example, VWX, they all fall along or lie along the same line. So in this example, we have two redundant vectors. Okay, X is redundant and W is redundant. These are both redundant. And you can see what we get. If you take all possible linear combinations, you just have this line. We just get, this would be a line or a one-dimensional subspace in Rn. Even though I'm taking three vectors and taking all possible linear combinations, we can see it just fills out this line, okay, because two of them are redundant. So we only have one linearly dependent vector. So this is some geometric ideas about span. Now, let us do some examples. The first example, I claim that the span of these two vectors is not R3. Now we can use some things that we've discussed since then, I first mentioned span, about dimension. So we know R3, maybe I should put this in the corner. R3 has dimension 3. And any basis for R3 has 3 elements, has cardinality 3. Okay, more is true. For example, this is something we'll see as we work through some of these problems. We need at least 3 vectors to span R3, and no more than 3 vectors can be independent in R3. Okay, so here, I say the span of these 2 vectors is not R3. Well, these 2 vectors are linearly independent. You can see they're both non-zero, and the second is not a multiple of the first. But the span is not R3 because 2 vectors, the reason here, 2 vectors cannot span R3. We need at least 3 to span R3. So this is my reason. You see it's short, but it's accurate. 2 vectors cannot span R3, even though they're independent. We would be in a situation like this. They would be spanning a 2-dimensional subspace of R3, would be a plane through the origin in R3. Now, the next one, I have 3 vectors in R3, and I'm claiming the span of these 3 vectors is all of R3. Why would this be the case? Well, we can put them as columns in a matrix. 5, 0, 0. We have 3, 1, 0, 1, 2, 1. This has rank 3. And so this says the vectors are linearly independent. We know the dimension of R3. The dimension of R3 is 3. So these vectors are a basis. The vectors form a basis. And necessarily every basis spans. Basis means the collection is linearly independent and span. So these vectors span R3 because they form a basis. But I knew they formed a basis. Once you know the dimension of your subspace, any collection of that many vectors that is independent necessarily is a basis and necessarily spans. Also, once you know the dimension, any collection of that many vectors that spans necessarily is a basis and necessarily is linearly independent. Okay. Well, the next question, you notice all I did was I took these 3 vectors. So these 3 span. I've already justified that because they are a basis. But I add one more and they still span. So the first 3 form a basis. So the collection spans. But I have an important but here that I'll make this as a note. 4 vectors cannot be linearly independent in R3. It's too many. You could see that if you put these as columns in a matrix, and that matrix will not have rank 4. It can't because there's only 3 rows. 4 vectors in R3 cannot be linearly independent, but they still span perfectly fine because the first 3 span. Cannot be linearly independent. That was an important comment. Now, this next one, you might recognize these vectors. We saw them on a worksheet. I'm claiming this is not a basis for R3, and it very much is. Well, the quickest reason to see that is similar to the one above. We can just say the reason this is not a basis, that 5 vectors in R3 cannot be linearly independent. Cannot be linearly independent. Now, there is another question I want to address here. These cannot be linearly independent. So without a doubt, not a basis. But the next question is here. Is the span of these vectors equal to R3? Now we haven't addressed that. And this is an important comment here. We have not yet answered this question. Just because they're dependent, linearly dependent, it doesn't mean the span's not R3. Because, for example, here's a collection of linearly dependent vectors, but the span is all of R3. It all depends. We don't know. So how can we figure out if the span of these 5 vectors equals R3? Well, one option, and I'll mention more than one option, but the first one is just remove the redundant vectors. This is what we had on our worksheet, was to spot them and write them as the linear combination of the ones that came before. So which ones are redundant? Let's see, redundant, redundant, redundant. Once we do this, what's left, if I label this, say, V1 and V3, so V1 and V3 are linearly independent, and all I've done is remove the redundant vectors. We have the same span. With the span of these 2 vectors will be the same. This is equal to the span. Well, now let me label the other ones, say V2, V4, and V5. The span of those 2 vectors will be equal to the span of all 5, because all I did was remove what's redundant. If you're starting to get confused, let's go back and look at the geometry right here. You see, here I had 3 vectors, and I can remove the redundant ones, and then what's remaining is the independent ones. Here it would be V and W. We have the same span. And similarly here, where I had 2 redundant vectors, I'm calling them X and W. If I remove those from my collection, what I'm left with is a linearly independent vector, same span. Okay, so that's what I did here. You can remove the redundant vectors. Now I have a collection that's linearly independent with the same span. But you see, We have a linearly independent collection and it spans. Therefore, this is a basis. So that means this collection V1, V3 will be a basis for, let's call this V. And so the dimension of V is 2. 2 elements in a basis. That's the definition of dimension. Okay, we have a 2-dimensional subspace. Not a chance. Is that R3? V cannot be equal to R3 because, well, R3 is 3-dimensional. Or you could say 2 vectors cannot span R3. Now, this is wonderful. We've solved the question. The answer is no. The span of those 5 vectors is not all 3 R3. It's some 2-dimensional subspace. But generally, it can be tricky to spot redundant vectors visually. This example worked out really nicely with zeros. We could spot them. So another way that you could do this, and we did this example in class, is you could figure out that the dimension of this subspace V is 2 by putting these vectors in columns as columns of a matrix. So let's do this. Okay. You note that the image of this matrix A gives me V. If I call this A, let's note the image of A is my subspace V. Okay, that's sort of by definition. You take all linear combination of the columns, but also you see just with one row operation, take minus row 1 added to row 3, we realize the reduced row echelon form of A. Well, we'll have a row of zeros at the bottom. 1, 2, 3, 4, 5. And then we have 2, 4, minus 2, 1, 0, 0, 4, 3. And you see, oh, actually, this is just row echelon form. It's fine. It's good enough. We are in row echelon form. It's not reduced because of the 2 there. But we are in row echelon form. And this is enough. You see the rank of A is 2. And this says the dimension of V, which is the rank of the matrix A, is 2. So once again, V cannot be R3. You see, there were 2 different ways you can realize the dimension of the span of these vectors. One was removing redundant vectors until what's left is a linearly independent set. And the other was just put all the vectors as columns of a matrix, figure out its rank. So I hope this extra discussion video about span and the examples was helpful for you. Thank you so much.